Hi, welcome back to Math 125 Introductory Statistics. This is week 3. We're going to talk about the normal distribution. This will cover chapter 5 of our textbook. Okay, so you remember that from the last lecture we talked about the SD as a measure of spread. It tells you how far away the numbers are from the average. Most entries in the list will be somewhere around 1 SD away from the average. Very few will be more than 2 or 3 SD away. So as an example, at least as far as application, things tend to center around the average. So for example, if I look at heights of women over age of 18, this is an actual data set. And notice the vertical line here is the average, which is 63.5 inches. And then notice that the shaded area represent 95% of the women in the study. And it is, if I look at the lower range and then the higher range, all these heights are within 2 SD away from the average. In this case, 2 SD is actually about 6 inches. So 95% of the people are within 2 SD away from the average. And so this is kind of true for most of the data set that we study. And there's a special distribution or a special histogram known as the normal distribution, sometimes called the bell curve. That is a histogram that occurs naturally in many situations. For example, scores on SAT or GRE or IQ scores. So the bell curve is symmetrical. Half the data is to the left of the average or the mean. The other half is to the right. And yeah, many of the applications in business, statistics, government studies, and all kind of natural phenomenon that follow this distribution. So for example, if I look at heights of people, pick a random set of people, find the heights of people, blood pressure of again, a random set of people, points on a test, IQ score, salaries, lifetime of light bulb. Look at the tons of random light bulbs. How long does that light bulb last? Of weights of loaves of bread, for example, even making bread, it's a machine that make mistakes. They follow this distribution. And so really kind of interesting that this distribution is kind of the natural way that things happen to distribute themselves. So again, if you look at IQ score, for example, most people have a certain average IQ score, and a lot of people kind of cluster around that average. Very few people would have high IQ score, and very few people would have low IQ score. So this is kind of a natural way that things kind of happen to fall. Heights of plants, for example, pick a certain flower, a plant or something, and then look at the heights of all the randomly sampling heights of that one plant, and we have the height curve following this distribution. So there's actually a mathematical formula for this curve, which is given here, but we don't have to worry about that formula too much. And so again, just based on data, about 68% of again, assuming that the distribution is this normal curve, 68% of the data fall within 1 standard deviation from the average. This mu symbol here is the average of the data set, and then notice 68% fall in the blue area, which is 1 SD to the left, 1 SD to the right of the average. And then this sigma notation is for the standard deviation. And then if I look at 2 standard deviation, 2 to the left, 2 to the right, about 95% of the population fall within that. And then similarly, in fact, most people, about 99.7%, fall within 3 deviation. So it's very rarely that you will fall outside of this, the 3 deviation left and right of your average. And notice the total area of this histogram is 100%. Okay, so as an example here, so for example, you look at a typical SAT score of a certain year. So say in one year the average was 505 on the SAT, I think SAT math score, for example, and then the standard deviation is 105. And so if I plot up all of the distribution of all the score, it looks something like this. And then if we look at heights of men, maybe the average is 69, the SD is 3, and then so here's the average right here, and then here's the distribution of all the heights of all the men. And so one thing to know about this is that these two problems look to be different problems, but they have the same exact distribution, up to maybe the numbers are slightly different, but the curve is exactly the same. And so even though the two things have different means, right, and different deviation, they have the exact same histogram. So what does that mean that they have the same histogram? Well, let's look at a sample problem. So again, same distribution as before. SCT score, average 505, SD is 105. The average height is 69. The SD is 3. Suppose we look at two questions. So we want to know maybe what is the percent of students who score 610 or lower on the SCT score. So that in other words, we look for the notation here is what's the probability or what's the percentage of people whose score is 610 or less. Here's another question that is for the men study. What is the percent of men whose height is 72 inches or lower? So what's the probability that x is less than or equal to 72? So these two problems seem to be kind of different problems, but turns out they actually have the exact same answer because notice that 610 and 72 are both exactly one SD or 1 standard deviation higher than the mean. For example, if I take 105 and add it to the average, you get 610. So that means that 610 is actually 1 standard deviation above the average for SCT score. If I take 3 and add it to 69, I get 72. So that means 72 is 3 inches or 1 standard deviation higher than the average. And so that means that because the two histograms are the same, the answer to both of these questions are the same. Is the same answer. So that's the key point to understand this week's material is that really these two questions are the same question. And once we understand that, we can solve any problem that are similar like this. And so if I look at the area below 72, 1 standard deviation. So again, 72 is right here. If we look at all the percent of people who are below that, you get 84%. Same thing for SCT score. Here's 1 SD away from the average. If we look at the percentage below that, it's exact same percentage, same shape. And so really this says that anytime we have a normal distribution, regardless of what kind of context it is, height, SCT score, IQ score, we can actually normalize it in a way and get essentially have a way to find the answer regardless of the context of the problem. And so how do I get these numbers? Well, we're going to talk about that in a second. Usually these can be found with a calculator, a fancy calculator, but we also can have a table. We can look up these numbers. So same histogram, right? Same shape, same answer, but different context. Okay, so that means that because these two pictures are essentially the same, we can just really ignore the numbers, right? Because it doesn't matter whether 72 is the average or the SD is 3, or that the average was 610, right, and the SD was 105, whatever that was. We want to treat these two pictures as exactly the same. So the way we do that is we're going to normalize these two pictures. And we're going to convert, instead of saying the mean is 69 or 505, let's make the mean, the middle, be 0, because it doesn't matter whether 69 or 505 is the same shape. So let's kind of shift everything to the origin and make the average be 0. And again, because it doesn't matter that the SD was 505 or 3, right? Oh, sorry, it doesn't matter the SD was either 3 or 105. So let's normalize that by just dividing by the SD and make the SD be 1. So in other words, these two pictures is the same as this picture, where the average is now 0 and the SD is now 1. It's a normalized version that doesn't take into context, whether it's SCT score or height. This is just a typical standard curve that can be used for all problems. And so this is known as the standard normal distribution. And so these points right here are called Z-scores, and these points a measure of how far away from 0 from the average. They're measured in terms of SDs. So for example, this 2 represent 2 SD away from the average. This -2 is 2 SD to the left of the average. And the SD doesn't care whether the SD is SCT score or height. It's just an SD. It's a unitless. And that's a nice way to look at the problem without be bogged down by the actual details of the actual problem. And then we have a table for this, a table of all the value for this curve, and that can be used for all problems, regardless of the context. And so a value is converted to a standard unit, or the Z-score, by seeing how far it is away from the average in terms of the SD. So So for example, let's do some example. Suppose that again the height here is 69, the SD was 3, right? So 72, for example, let's convert this 72 into the Z-score or into standard units. So you want to know 72. We don't care that 72. We just want to know how far is this away from the average in terms of the SD. Well, this is 3 inches away from the average for 69. It's 3 inches above. And 3 inches is the SD, so that means that the 72 its equivalent Z-score is +1 because you are +1 SD away from the average. 66 is actually 3 inches below the average. So again, we don't care about the inches, we just care about the SD. So this Z-score, the Z-score for 66 is -1 because it's -1 is 1 SD to the left of the average. 75 is 2 SD because 6 inches away from the average. So the Z-score for 75 is +2. And then finally 70.5 is 1.5 inches, which is half of an SD. So the Z-score for 70.5 is 0.5. Again, everything is in terms of the SD. So the Z-score is the SD, is basically a measure of how many SD away from the average. So that way we can ignore the actual measure and do it in terms of the SD. So the formula for this is, if we want to do this more systematically, here's a formula. Take the old score, for example 72, subtract the average, see how far it is from the average. If it's positive, it's to the right. If it's negative, it's to the left. Then divide by the SD. That tells you how far is it away from the average in terms of the SD. So for example, 72 minus 69 divided by 3 is 1. That's how I get the +1. So this is the formula that can help you find any Z-score, but it's important to understand these examples because you have an intuition for how the SD is obtained. So here's an example. So again, the average height is 69, the SD is 3. So we want to find the percentage of men whose height is less than or equal to 71 inches. So how do we do that? Well, here's the information. We want to compute this problem. So first we're going to convert 71 into the Z-score. So we use that formula, right? So 71 minus the average, 71 minus 69 divided by 3 is 2/3, which means that the Z-score is 0.67. That says that 71 is about 0.67 standard deviation above the average. And now, instead of doing this problem, which is what's probably the x is less than 71, we convert into another problem. And that problem is that what's the percentage that the Z-score is less than or equal to 0.67. And so we normalize the problem so that we don't care about the actual height problem. We care about now a normalized problem. And this normalized problem, we can use a table for, or we can use the calculator for. So I'll post this Z table that I'll show you in a second under course material on Blackboard. But now we convert a height problem into a Z-score problem. And the Z-score problem, as I said, have a nice table that we can look up the answer. And so that way, if I have a different problem that has to do with SAT score, same thing. I convert it into a Z-score and look at the Z table rather than try to do that problem, which we don't have a table for. But the normalized problem, the Z problem, does have a Z table, and that's what we want. And so the Z table, this is how the Z table works. The Z table that I will upload on the as a PDF will tell you that. By the way, there's another Z table from the textbook that is a little bit different, and so that table is actually a little bit harder to use. It doesn't have the necessary decimal accuracy that we need for web work. And so for our class, we're going to use the Z table that I upload as a PDF. So again, we will not be using the Z table from the textbook because of accuracy reason. So the Z table tells you the area to the left of the Z-score. So that's an example. So again, this is only a partial Z table. The Z table I upload has actually 2 pages. But for example, if my Z-score is, so if I'm trying to do this problem, what's probably that x is less than 71, which is the same thing as what's probably that Z is less than or equal to 0.67. Well, I'm going to look in the table for 0.67. So on the left side here, we're looking for the 10th place, right? So 0.6 is here. On the top, I have the hundredths place, so the 0.07. Together, 0.67 would be this number right here. And so this says that, this table says that the percentage of people, right, whose score is less than 0.67, again, whose Z-score is less than 0.67, is 0.7486. In other words, about 75%. So that's how we read the z-table. We look at the left column and the top column, combine it to get the actual z-score, and the number there tells you the percentage, right? Again, you have to convert the decimal. It's a decimal, but you can convert it into a percentage whose z-score is less than or equal to that number. Okay, let's do another example. Suppose you look at SCC score, the average is 535, the SD is 100. We want to know what percentage of students who scores greater than 500. So again, I convert the 500 into a z-score, normalize it. 500 minus 535 divided by 100, you get negative 0.35. That means that this score 500 is about 0.35 SD below the average. So now, instead of doing the problem of what's the percentage of students who scores bigger than 500, we convert into a z-score problem. What's the percent of students whose z-score is bigger than negative 0.35? Okay, so this is where we have to do a little bit of a trick. The table only tells us the score below a certain z-score. It doesn't tell us the score above a certain z-score, which is the actual problem. So but this is easy because remember the total area is 100% or 1 as a decimal. So if I know the area to the left of a score, I can find the area to the right by subtracting it from 1 or from 100%. So to find the probability that z is bigger than or equal to negative 0.35, I take 1 and I subtract the percentage or the probability that z is less than or equal to negative 0.35. And so if this probability, for example, is about 36%, then the other probability must be about 63%, 64%. Yeah, so we just subtract it from 100%. So that's how we do that problem. And then another problem is that what if I want to know the percentage or the probability that people have scored between two numbers, maybe between 410 and 700? Then there's another trick for that. So we convert both of these score into z-score. So 410 minus 535 divided by 100 is negative 1.25. Z2, the 700 correspond to 2.15. So 410 is the same thing as negative 1.25 SD to the left of the average, and 700 is 2.15 to the right. So now we want to find this problem. What's the probability that my score is between 410 and 700? Well, normalizing that, well, that's the same thing as okay, let me show you. I think the best way is to see a picture here. So I'll come back to this formula. I'll show you the picture here. If I want to find the probability that I'm between two score, that's the same thing as find again, my z-table only tell me the probability that is less than a certain z-score. So the z-table only tell me this graph, not this graph. So I first take the probability that the x is less than 700, which the z-table tell me. Then I take the other graph, which tells you the probability that the x is less than 410, which the z-table also tell me. Take this and subtract that one. Right? If I take this and subtract this, I get all the percentage of people who are between those two. Right? And so again, right, to solve this problem, I have to break it down to two problems and then subtract the two pictures, the two probability. So that means that's why we have this, right? The probability of between 410 and 700 is all the people that is less than 400 minus all the people that are less than 410. And then I convert these into z-score because we found the z-score, and then we look up in the z-table and then subtract the two probability. So that's how we do that problem. So here's another example. What if I have SCC score again 535, SD is 100. What if I want to know the 95th percentile of the score distribution? So the 95 percentile, this is what you typically get when you get the SAT score. It's basically the score. So again, the 95 percentile score is the score below which 95% of the population fall. So for example, if this percentage is 95%, I want to know what score is that, right? So in other words, what score do I have to get to do better than 95% of the population? So this is kind of a backward problem. Okay, so I want to know this. What is my S, my score, so that the percent of people who scores below that is 95%. So I'm trying to look for S. So notice this is the opposite problem as before, because before I know S and I'm looking for the percentage, but now I know the percentage. I'm kind of have to backtrack and find the score. Okay, so first thing is that I need to look inside the z-table to look for the percentage, which is 95%. So here it is, right? Again, I don't want to look outside. I want to look inside. Look for the 95%. So this, because that's what the percentage is inside the table. So based on so this is look around it. This is kind of the closest one to 95%. So if I pick that one, then I notice my z-score is 1.65. Right? See, I'll take this number 1.6 and the 0.05, and my z-score is 1.65. Then from that z-score, I can backtrack. So now that I know, so I need again. I have this revision problem. I don't want to know what score it is, so that I score better than 95%. I convert that into a z problem. I'm looking for a z prime, so that z prime give me 0.95. So from the table that I just showed you, that z prime was 1.65. So now I have this formula that I had earlier, and I can now backtrack. Before I have this s score, and I'm looking for z, but now I have the z score, which is 1.65. I'm looking for the s score in this equation, so I gotta solve for s. So I can cross multiply 100 times 1.65, and then I add 535 to get s. So that says the s must be 700. So 700, right, would solve this equation. So that means that if you want to score better than 95% of the population, you need to score 700. Okay, the average and the SD can be used to summarize data that if it follows the normal curve. But there's some distribution where it doesn't follow the normal curve. For example, income, right, doesn't follow the normal curve. For example, income, here's a data set from 2004. If I look at this, right, this is not the normal curve. It's not symmetric around some center, right? It actually has a long tail here. So if it's not normal distribution, then we can't use the normal curve. In that case, we use another measure. So by the way, if I try mistakenly use the normal distribution, then I get that that 7% of the family have negative income. Again, so this doesn't make sense. If I impose the normal curve here, right, then it doesn't work. So this is not a normal curve. So if I mistakenly use the normal curve, I get something that doesn't make sense. And so for this reason, we don't want to use a normal curve here. We want to use another way to measure percentage. We use something called the percentiles. So a better table is to look at a percentile table like this, where, for example, this 10 represents 10 percentile, and so that means that if your income is 15,000, then your income is higher than 10% of the population. If your income is 54,000, then your income is higher than 50% of the population. By the way, 50% means that you right in the middle. 54,000 here would be the median, right, from the last lecture. If your income is 135,000, your income is higher than 90% of the population. Again, this is if I'm income back in 2004. So percentile would be another way to kind of look at the. So instead of trying to do a normal distribution, a percentile table would be more appropriate as a way to understand that data set. Okay, let's talk about change of scale. If you have a list of numbers and you want to add the same number to every entry in the list, then that number gets so the question is that if I have a list of numbers and I know the average and the SD, and I add the same number to every entry in that list, how does that affect the SD? Well, it actually turns out the SD does not change, even though the average gets added by that number, right? And the reason because the deviation is a measure of how far you are from the average. If you add the same number to every number, then the whole distribution gets shifted to the right or left, depends on what you're adding or subtracting. So that shouldn't affect the spread of your data. Again, if I take a distribution, for example, like this, whether it's normal or not, and I just add 30,000 to everybody's income. That means I take the same picture and I move it to the right by 30,000. Then that shouldn't change my SD, because the SD is the measure of spread. If I move this picture to the right, that doesn't change the spread, right? It changed the average by 30,000, but the SD would not be changed. So that's what this is trying to say, is that when we do a change of scale by adding everything to the same number, that does not change the SD. If you multiply every entry by a number, then the average and the SD gets multiplied by that same number. And the reason is because if I multiply by a number, I'm stretching this out, I'm spreading it out by the same factor. For example, multiply everything by 10, then all the income will be spread out by a factor of 10. And so both the SD and the average would be multiplied by the same number. There's only one exception, is that you multiply by a negative number, then that wipe out the sign, You have to wipe out the sign before applying the SD. But that case is a special case. We don't have to worry about that case. So that's an example of this. The average of this list is 4. The SD is, if you compute the SD is 2. So if I take this list and I multiply everything by 3 and then add 7, I get the following list, 10. So again, multiply by 3. 3 times 1 is 3, plus 7 is 10. 3 times 3 is 9, plus 7 is 16. So again, I'm taking out every number from this first list, 1, 3, 4, 5, 7. I multiply by 3, and then I add 7. So the question is, how does that affect the average and the SD? Well, let's figure out. Well, first of all, if I just well, okay, let me go back. So again, we saw earlier that if I multiply by a constant, then that affects the average and the SD by that same factor. But if I'm adding a number that only affects the average and not the SD, so in other words, multiply by 3 and adding 7, that will affect the average by multiplying by 3 and adding 7. So if the prior average was 4, then that average multiplied by 3 is 12, plus 7 is 19. So the new average is 19. So when you ever multiply or add, both the operation will affect the average the same way. So the old average is 4, the new average is 19. The SD, however, is only affected by multiplication, as we saw earlier, right? Adding 7, shift everything, doesn't affect the SD. So the SD is only affected by the multiply by 3 operation. The old SD was 2, the new SD is now 6. And of course, as a way to check, you can also recompute both of those using this new list, and you see that these are the answers. But this is a shortcut so that you don't have to recompute the SD. Another way, okay, so let's another way to think about this is to think about this as standard units. So let's convert these numbers into standard units. So the first list, the average is 4, and so converting these numbers into Z-score is this. So 1 is negative 1.5 SD away from the average. 3 is negative 0.5 away from the average. 4 was the average, so 4 is 0 SD from the average. 5 is slightly bigger than average, is half a SD above the average, and 7 is 1.5 SD above the average. So again, all these are Z-score correspond to those values. Again, Z-score tells you how far you're away from the average. And then for part B, same thing. I find how far are they from the average, and notice they're the same numbers. In other words, even though I multiply by 6 and add, right? I changed my scale, but my SD still have not changed. That's kind of the lesson here. Even though I scale everything by multiplying by 3 and then adding 7 as I did earlier, all these new score, they're the same SD away from the average. Even though the SD for the second case is bigger, it's still an SD, right? So for example, 1 is negative 1.5 SD to the left of the average. And again, that SD was smaller. That SD was a 2. 10, however, 10 is actually 6 away from the average. That SD is bigger, but 6 is still only 1 actually the SD is 6. So when I look at 10 is still only negative 1.5 SD away from the average if my SD is the new 6. So even though 10 is kind of seeming to be further away from the average than before, it's still only 1.5 SD to the left of the average. And this is the reason why we like the SD, because it's not affected by a scale. Right? Even though I multiply by 3 and add 7, the SD itself is not affected by it. And that's why it's called the standard units or normalized units, because it's not affected by those scaling, which is important because there's some problem where we don't want to be affected by scaling. So here's an example. Actually, no, let's summarize first. If I add the same number to every entry on the list, it add a constant to the average, but it does not change the SD. If you multiply every entry on the list by the same positive number, it multiplies the average and the SD by the same constant, and these don't change the scale. Okay, great, thank you.